Okay. Yeah, you can see my screen, right?
Arya, we're good. Yes.
Okay, sounds good. Okay, so today we're just going to be briefly going over stress analysis and how to make renders on SolidWorks. The stress analysis part is going to be very basic, and it's for team members and students who haven't taken stress analysis or aren't familiar with the different types of stresses. Maybe they're not in the ME major, so this is going to be a recap on the different types of stresses that exist. And then also we're going to be talking about how we can find the factor of safety against yielding, which is very important, and we'll talk about what that means. And we're going to make a render on SolidWorks, and rendering, I think, is pretty cool. When you make a model on SolidWorks, it looks pretty bland, but if you make a render, it looks really realistic. And so we'll go over that as well. So we'll be making a render for this Hyperloop pod cover. So, okay, so there are basically three main types of stresses. And if you've taken any of the ME classes, they would have covered this. There's the normal stress, bending stress, and then torsional stress. So if you look on the bottom, you can see these three stresses laid out in chronological order. So normal stress is basically whenever you pull or push on something. So let's say you have a rod and you're basically pulling on the rod. There's going to be some stress in the axial direction or in the direction of that force. And that's considered the normal stress. And to determine the normal stress, you have to calculate force over the cross-sectional area. And as you can see by that, normal stress, or any stress in general, is just basically another term for pressure. So what would the pressure be if a force is exerted on an elongated beam with, number one, it would be this equation, this force over area, which is the normal stress. Bending stress is a little bit different. When there's a moment induced on any object, like you see here, where there's some bending going on, you'll see tension. In this case, you'll see tension on the bottom, because you can see that the bottom middle section of this beam is getting elongated, while the top middle section is getting compressed, or it's getting closer together. So this is going to be the bending stress. And to determine the bending stress, you use the second equation, which basically is bending stress is equal to the moment acting on the body times the vertical distance away from the neutral axis, and we'll talk about that later, and the moment of inertia around the neutral axis. So what Y and I basically are talking about, they're referring to the cross-sectional area of the beam. So right now, we only see the length and the height of the beam, right? But since this is a 3D object, there's going to be a width or the thickness of the beam as well. So when we look at that cross-sectional area of the width or the thickness and the height, you're going to be able, you'll have to find the center of that cross-section. And that's going to be your starting point. And from there, if you want to find this tension at the top, right here, like what I was talking about, at the very top, you see compression, and then at the very bottom, you see tension. If you want to find that, you basically have to, the Y value is going to be from that center or the centroid, and then going from that to that point. So if you want to go to the very top, then you just basically, Y is just going to be from the center to the very top. And if you want to go maybe not to the top, only 50% there, then just be 50% of that distance. And as you can see, that kind of this bending stress decreases linearly with the vertical distance. So the maximum bending stress occurs at the top and the bottom, the very top and very bottom, and then it decreases, in the middle. The moment of inertia, there's an equation for the moment of inertia. It differs based on the geometry. So if it's a rectangular beam, then it's going to be 1/12 base height cubed. You don't have to remember that. If you go online, you'll find an entire list of how to determine moment of inertias for different geometries. It's going to be different for a cylinder. It's going to be different for, like I said, a rectangular elongated beam. But you can find that online. And then the last one that we're going to be going over is torsional stress. Torsional stress is when you induce a moment, like a twist, in, it doesn't have to be a cylindrical beam, it could be a rectangular beam as well. But in this case, it's a cylindrical beam. And if you induce a, like a twist or a moment to that object, you're basically going to get some torsional stress. If you think about it intuitively, if you get like an eraser, and if you like twist the eraser, you're going to see some shear. You're going to see some shear stress. There's going to be this tendency of that eraser trying to rip at the middle, right? So that's what the torsional stress or shear stress is about. To determine that, you multiply the torque by the distance from the neutral axis. So the neutral axis is from the center, again, just like similar to number 2, from the center of the circle to whatever radius you're interested in. So the maximum is the surface. So maximum radius, or what the actual radius of that circle, that's going to be your maximum, or you can choose another length. And then here you divide that by J, and J is the polar moment of inertia. And you can also find polar moment of inertias online. It's going to vary depending on the geometry. So, but the one thing that it's important to point out is that this particular equation is used for cylindrical bodies, like a cylinder. If it's not a cylinder, then there's going to be different equations for it. And now there is one more stress type, and that's called transverse shear stress. Now, transverse shear stress, I'm not going to be going over that because it's a little bit more complicated, and you would need to kind of understand how to deal with moments and deal with the neutral axes. And usually a lot of times it's disregarded just because its effects are minimal in comparison to these 3 stresses. So now I'm going to go over von Mises stresses because when you look at SolidWorks models and when you do the simulations, I showed you how to do a simulation last time where we stress simulations where we calculated the maximum stress at given points on a body, depending on the applied load. The stresses that kind of SolidWorks gave us were von Mises stresses. So there was a bar, of like a range of different stress values, and they were all von Mises stress values. It's very important to understand what von Mises stresses are, because in industry, you're mostly going to be using these particular stresses to assess whether your body is appropriate for its function, whether it's going to fail at a given load. So basically what the von Mises stresses are as per their definition, they're basically a criterion that is also called the maximum distortion energy criterion, which helps to predict failure of a body. So it basically states that the maximum value of distortion energy per unit volume. So you understand. So we know what density is, which is just mass over unit volume. In this case, it's the distortion energy per unit volume. So if you think about a load being applied to any object, there's going to be some compression or tension. And as you can imagine, once anything is compressed or stressed, pulled or pushed, there's going to be some sort of displacement going on. So you can see that there's some amount of energy being inputted into that particular object when there's a force applied. So there's going to be some amount of distortion energy. So the distortion energy per unit volume needs to be smaller than the amount of distortion energy that would cause yielding. And yielding is just basically when there's it's when we look at metals and when we look at different types of objects, there is so much applied load that or stress that can take After a certain point, it's going to start yielding, or there's going to be permanent changes to its geometry, to its length, and that's what yielding basically is. You're going to see a bottleneck effect on certain types of metals. You're going to see fracture, so yielding basically accounts for all that stuff. So the way we want to kind of go about when we're designing things is we use this simple distortion energy formula, or von Mises formula, and basically it's going to be the amount of stress that you have squared plus 3 times the shear stress squared. And then you square root that and you get the von Mises stress. And then you divide that by the yield stress, which is given for different materials, and you find n, which is a factor of safety. So factor of safety accounts for any errors that might occur, or it's basically a room for error. So we use this formula to find von Mises stress, and then we compare that with the yield stress. So if this is less than the yield stress, we're going to have a non-fraction number. So it's going to be like a whole number. Basically, that means that our model, or our body, is safe with the applied load that we're giving it. Because so for instance, if sigma was like 500 and SY, or the yield stress was like 1000, that means we have factor of safety of 2. So like we thought that, okay, there's going to be 500, there's going to be a stress of 500, but there might be a chance we increase that amount because, I don't know, there might be some room of error, there might be some fluctuations, and then we account for that in order to avoid any catastrophes like, damaging a system or breaking something. So that's why we have factor of safety. And so when we're doing the Hyperloop pod, when we're building the Hyperloop pod, or whenever we're out there and building or designing something, there's something to be mindful of. So we want to find the von Mises stresses using the maximum load that we think that object is going to experience when we're using it. And we find the von Mises stresses, and we find the yielding factor based on the material of that object. And then you find the factor of safety to make sure that that the amount of force that we're applying, or that it's going to experience, doesn't even come close to what it can actually take. Otherwise, it can cause problems. And this equation for von Mises stresses only deals with 2 types of stresses. Sometimes there might be multiple stresses involved, and for that there's a larger equation that requires like calculations on Mohr circle and stuff like that. But that's more in depth, and for this presentation, it's appropriate to just kind of go over the simple distortion energy formula to get an understanding of how to approach stress calculations. Now, the fun part. So renders are basically an illustrative way to show a design concept to a customer or client. So I have I have 4 images in the bottom, and you can see that the first 2 are just SolidWorks, SolidWorks parts, right? These are just screenshots, and they look pretty simple. But on the right-hand side, you can see like it looks much more professional, and it looks much more presentable, right? So if you're gonna go present this to a client, or to an investor, or to a customer, you don't want to show them this. You want to show them this because this is how it's actually going to look in real life. The other one looks more of like a cartoon drawing or something. This one looks much more realistic because basically, when we're doing these renders, it takes into account 2 things. It takes into account the shadows, the colors, but it also takes into account the textures of the different materials that we're using. And this is actually from a project that I'm doing in my design class, and we're making a solar panel optimizer. So these are, these are the same parts, but this is a render, and then this is the SolidWorks assembly. So Now, now we're gonna basically transition over to making a render for the Hyperloop pod. I'll show you how to do it step by step. If you have any questions. Is a commotion gone? I didn't see that comment. But yeah, so we're going to be going over renders step by step. And if you have any questions along the way, just ask, you know, and I'll make sure to look at the comments. Okay, I want to stop sharing this. I want to transition over to SolidWorks. Okay, so here's the pod. Now, one of the things that's different when we're doing a render for this compared to when we're doing a render for another assembly or another part is that this was actually taken from Fusion 360 and converted to a step file. And so there might be some limitations when we're trying to make, basically when we're trying to make a render, but it should still work. So let's basically get started. So if you go to SolidWorks add-ins, go to Photo View 360. And then now you're going to have this under the taskbar, there's going to be this option for render tools. Okay. And now you can press this to edit your appearance. Right now, it just basically everything's the same color, same texture. It looks pretty bland. I mean, you can still do a render for this, but you want the render to be as realistic as possible. Kind of highlight all the texture that's going to have. So when you go to edit appearance, it's just going to give you options to change the color. So if you want to do that, say, yeah, see, so, we can change the color for the top, right? So actually, let's give it more of a, I don't know, this is just like a color that I've chosen, this might not be how the actual print might look like, but this is just a, here's gonna be added. Okay. Let me see. So we got the top part. On the bottom part, we can also change the color. I think you want me to do it separately. So yeah. Okay. Yeah. Now, if we are okay with the colors, then we can, that's okay. And now we see that the colors changed. Now, let's look at the I-beam, right? So the I-beam basically is this color. That might be the real color, it might not be. Usually I-beams are made out of aluminum, or at least in our case, they'll be made out of aluminum, and they're basically gonna have more of like a whitish color. So what we can do is we can press on the part here, and instead of changing the color, which we can do, so since we want to kind of capture the kind of the glossy coating of aluminum, we can go to material, and we can basically change the material. So in our case, now this was the distinction that I was trying to make. Since this was a assembly file that I took from SolidWorks, it's not gonna, it doesn't have all the functionalities. And now I'm not sure why it only lets me pick from these different materials. But if you were making this on SolidWorks, you know, you're kind of familiar with being able to, let me see. Yeah, you would be familiar that there's a way where you can change the material for this, and when you do that, there's going to be many more options that you can choose from. In our case, what we can do is we can improvise, and we can say that it's going to be nickel, because nickel looks similar to aluminum, right? In terms of color and texture, and they're both glossy, and they're both, you know, kind of like white metals. So it should come out as the same. Well, let's just choose nickel for this. Okay. So here we have everything finished. Now we can go to integrated preview. And now it's going to ask you to add a camera. And I would recommend adding a camera because this basically helps you kind of capture the image in a particular perspective, in a particular direction, instead of, you know, it's easier to use a camera to do that. So, like for instance, let's see. Okay, so here we have a camera, right? And we can position this the way we want. I mean, it looks good right now, so I don't think there's anything to change. However, if you wanted to, you can change positioning of the camera. You can change the orientation. You can enlarge. You can bring this closer. Or you can bring it further away, right? So you can make some changes using the camera. Once you're okay with it, this looks pretty okay. So I'm just gonna press OK. And now I'm left with this. Now you can press final render. Do you see this new screen that popped up? I might have to reshare.
Oh, no, I don't. Okay.
You see it? Okay, let me just. Okay, now you should be able to see it. Yeah, so it takes a while for it to kind of let me see. It takes a while for it to kind of finalize. But you can see that the clarity is much higher for this. If you look at the I-beam, there is a little bit more coarseness or a little bit more roughness to it. And that's just because metals are like that. The reason that pod cover looks a little bit more shinier is because we didn't really specify what this is going to be. So I think by default it's chose to be an arbitrary metal. But you can see this is the final product, and this looks much cleaner than what we had before. If we want to, however, I'm just going to show you guys one thing, and that is if you want to kind of change the texture or the glossiness of this, you can basically go to SolidWorks. Let me see. You can go back here and you can go to the pod cover. Okay, so top cover, and you can change the material for this. Let's see what happens if you choose ABS. Okay, and for bottom cover, we can choose ABS as well. Now ABS, okay. Were you able to see the screen after I stopped screen sharing and then I put up the other one? Oh, okay. Okay, let me see. Okay, can you see SolidWorks right now? Okay, okay, good. Then we'll do that part again. But basically, it's good, I guess, because we're gonna be making some changes one last time to the pod, and then we'll do the rendering. So for the bottom cover, I'm just changing this to PLA because you weren't able to see what the final results were. However, basically the pod cover had a very shiny coating. It looked like it was made out of metal, but since we're going to be using plastic, I'm changing this to ABS because this is the only option they give us that's close to what we're going to be using. So we're going to be using PLA, but ABS is another plastic that people use to 3D print. So it should work as well. So we have this. Now, you can do final render. Usually when you use other SolidWorks add-ins like simulations or rendering tools, it takes a while for things to load. So let's work it. Okay, let's see. Material, EBS. Bottom cover. Okay. SolidWorks is running pretty slow. Yeah, the screen did pop up, but it's been slow, so I guess it didn't really show up. It didn't show up on my end either. So I'm trying to see what's going on. Okay, so we have this. We're changing this material to ABS. Bottom cover. Okay, this is already ABS. Here we go. Yeah, here we go. Yeah, so you can choose between the yeah. Okay, I see what the problem was. So remember how I said that you can only choose from a certain different metals? That's not actually the case. What you can do is you can just go down here. I guess it actually works. So you go here, you go to edit material, and you can choose from a wide range of materials. They still don't have PLA here, so we're still going to be using EBS. Okay. So this is ABS. Top cover. Change this to ABS. Okay. Now, I'm going to exit the preview window. And then I'm going to rerun the render tool. Okay. For some reason, SolidWorks isn't acting weird right now. But see, I'll have to reopen it, I guess. File. Yeah, for some reason, the SolidWorks is crashing. Let's see if I can download this again. Sometimes this happens. I'm not sure if you're all familiar with like when you have those notifications saying that you have low resources on SolidWorks. Usually when something like that happens, basically things begin to crash, especially when you have so many parts. Yeah, Chris? Oh, okay. Okay. Let me see. Okay, okay. Yeah, for some reason, my screen share stopped working. And SolidWorks crashed again. Let me try reopening this. I at least want to show you all how to make the render. I might not be able to edit the materials and everything right now, but you all, I think you all experienced with changing the material properties and color as well. So that shouldn't be an issue. It's just really understanding how to use the rendering tool. So I'll try to see if I can get that up. Let's see. Okay, I think it's working now. Let me share my screen again. Okay, so let's just quickly go over this again. We have the I-beam. And where do you, okay, we have this. We go to drop-down menu, go to materials, specify the material as aluminum, go to edit material, go to aluminum alloys, choose an aluminum alloy. Okay, so now you can see that there's been a change in color. We do the same for the front one. Go to drop-down menu, go to materials, edit material, aluminum again, 1060 alloy. Okay. So now we have that. Now we're gonna look at the pod cover. So the pod cover is made out of plastic. We can go to here. Okay, so we're done with the I-beams. We can close these drop-down menus, and we can go to top cover. We can specify the material. For this case, I'm going to specify, I'm going to go to custom materials, go to plastic, the custom plastic. You might also, you know, or you can go to, yeah, I mean, in this case, I would just choose custom plastic because they don't really have many options for plastic. Yeah, so I'm just going to choose custom plastic. Yeah. Or I mean, I guess they do, but a lot of them, like if you choose ABS in this case, actually, let's see what they do. What happens if you choose ABS? Okay. Yeah, I guess we can choose ABS. Sometimes it'll give you like a transparent color if you choose a certain type of ABS. But since this is going to be like a non-transparent part, so we can choose simple ABS. I think ABS PC was what I chose last time. That's what gave me that's why it gave me a, you know, like a clear part. But use material from the bottom as well. Plastics, ABS. Yep. So there is our pod. I guess if we want to, we can also give color to these as well. They don't really show, but I think just in case it does, everything will be consistent. Let's see. Okay, so these two, let's make them aluminum as well. Okay. Now the entire I-beam is aluminum. The top cover is ABS. We don't really need to worry about what's inside because, you know, we're not going to be able to see the inside anyways. Now what we can do is we can go to SolidWorks add-in, go to Photo View 360, go to Render Tools. You can go to edit Appearance and you can change the colors. I'm not going to do that because it might crash again. So I'm just going to go straight to rendering. I think this perspective looks good. It's isometric. You know, you can see it in like a 3-axis angle. You can see, you know, you can see most of the pod, and you can see the aluminum beam that it's traveling on. So I think this looks good. I'm gonna go to final render. I'm not gonna add the camera. Like I said before, camera is to change perspectives. It's useful, but I just don't want to crash it. I don't want to crash the system again for this demonstration. So I'll just continue without it. And now, okay, do you see the pop-up now, or do you guys not see it? Do you guys see the pop-up? Or do you see the other screen where the renderings, where we're making the render? Black screen. Okay. Let me stop screen sharing and maybe I can screen share that particular page. You now see it? Okay, good. Yeah, so this is a render, right? I know that the colors are not, flashing too well. But what we have here is that we can look at the pod cover and it looks like plastic, right? It looks like, heavy ABS white plastic. And the beam, you can see the roughness on the beam, you can see its texture, and you can see that it looks like aluminum. So basically this is kind of a drawing that you can give to someone and say, this is exactly how it's going to look like, right? So this is a very cool and important tool, right? This takes us out of the engineering realm of design and into more of the marketing and more like investor relation type of part of the design phase, because we use SolidWorks to have a better understanding of how a system might work, but if you want to make it pleasant and appealing and show people that, hey, this is what we're making, then this is a good tool to use. Okay, and it seems like you said someone that they're not experienced with that. Were you talking about changing colors or changing materials? Or if anyone has any questions about this process? Okay, okay. Yeah, so if you want to change materials, just go drop down menu, right click on material, edit material, and you can change. They have a wide variety of different materials that you can choose from. Right. I think that's pretty much it. If anyone of you has any questions, then feel free to ask right now. I know that you weren't able to see the other renders that I made, but they are here on the bottom. So this is what happens when you change the material. So here you can see that this looks like plastic, right? It's non-glossy, looks relatively thick. It looks smooth. Here's what it would look like if it's perhaps made out of like a metal, right? You can see it's glossy, still smooth, but you can see that there's more of a metallic texture. Here's what it would look like if you're using something like a transparent material. That's what I was talking about before. I think it's ABS PC. I think that's clear, transparent. I might be wrong, but one of the materials, if you choose that, you can get more of like a transparent, you can get like a transparent body. So it just depends on what material you choose. Yeah, so looks pretty nice. Any questions? Okay, so if none of you have any questions about the stress analysis portion or the rendering portion, then I think we should be good. Right, thank you everyone.